Hello everyone, welcome to my course on electromagnetic theory and interference. In this session, we are starting our module 2, that is magnetostatics, and here we will see one of the laws that is governing our magnetostatics called Biot-savart law. So before going to Biot-savart law, let us understand the difference between electrostatics and magnetostatics. So the static electric fields or electrostatic fields are characterized by electric field intensity E and or electric flux density D. Both are vectors. Whereas static magnetic fields are characterized by magnetic field intensity H and magnetic flux density B. And we know the relationship between D and E, right? It is D is equal to epsilon naught E. If for a linear isotropic material space, my magnetic field intensity and magnetic flux density are related by D is equal to mu into H. Okay. We already know that electrostatic fields are created by static charges or the stationary charges. If the charges are moving with a constant velocity, a static magnetic field or a magnetostatic field is produced. And magnetostatic field is produced whenever there is a constant current flow. Okay, where there be a constant current flow in a direct current, right? So this current flow may be due to various currents like magnetization current in permanent magnets, electron beam currents in vacuum tube, or a conduction current in a current carrying wire. So the magnetic phenomena find application in a variety of day-to-day life things ranging from motors, microphones, compass, telephone bill rings, okay, advertisement display, magnetically elevated high-speed vehicles, memory storage, magnetic separators, etc. So there are two basic laws which is going to govern the magnetostatic field. One is Biot-savart law, other one is Ampere circuit law. We already know that Coulomb's law is the general law of electrostatics. Similarly, Biot-savart law is the general law for magnetostatics. Just like the special case of Coulomb's law, like Gauss's law, Ampere's law is the special case of Biot-savart law, and we can go for Ampere's law whenever there is a symmetrical current distribution. Let us see the Biot-savart law in detail in this session. The Biot-savart law states that okay, the differential magnetic field intensity, the DH, okay, it is produced at a point P by the differential current element ideal. There is a current element ideal. Okay, so because of that, there is a differential magnetic field intensity produced. So that is proportional to the product of the current element ideal and sine of the angle between the current element and the line joining the current element and the point P, and inversely proportional to the square of the distance between the P and the current element, right? So this is expressed mathematically as DH is directly proportional to ideal sine alpha by R square. If I remove the proportionality constant, it is going to be K ideal sine alpha by R square. My proportionality constant is going to be 1 by 4 pi instead of 1 by 4 pi epsilon naught in Coulomb's law. Okay, so we can apply this K value and we'll get the magnetic field intensity. So the same magnetic field intensity that we got here, I can rewrite in terms of cross product, because cross product I know we get ideal cross AR cap I can write, because in cross product only I will have the sine of the angle, right? By 4 pi r square. This AR cap is a unit vector, that is vector divided by its magnitude. So the direction, how should I determine the direction of my magnetic differential magnetic field intensity? It is by the right hand rule. If my right hand thumb points in the direction of current and the right hand fingers encircling the wire will show me the direction of magnetic flux, magnetic field intensity. So I can represent the direction of magnetic field intensity in two ways, by drawing a circle and putting a dot inside. That means the current or magnetic field intensity is outwards. Whereas if I put a cross sign inside the circle, it represents the magnetic field intensity is coming out of the page. Okay. Now let apart from the line current distribution that we have considered to understand the Biot-savart law, there are different current distribution like surface current, and volume current. Okay, K is the surface current density, which is represented by ampere per meter. J is the volume current density, represented by the unit ampere per meter square. So the source elements, whether there is a current carrying conductor, it is ideal. This is equivalent to KDS. Okay, surface current density into the surface area, differential surface area, that is equivalent to J into dV. So I can rewrite the Biot-savart law. Okay, ideal cross R or ideal cross AR cap by integral of the line ideal cross AR cap. Okay, I'm finding the magnetic flux, magnetic field intensity H. So to do that, see here we have written a differential magnetic field intensity. To find the magnetic field intensity, I have to integrate. So I integral over the line ideal cross AR cap divided by 4 pi r squared for line current, and this is surface integral of KDS cross AR cap by 4 pi r squared for surface current, and it is integral over the volume JdV cross AR cap by 4 pi r squared for the volume current. So AR is the unit vector pointing from this differential element of the current to the point of interest. Uh, Soon we will meet in the next session. Thank you, everyone.